Now, many of us enjoy the art of making electronic projects or repairing our own equipment, but this inevitably means soldering, and with the wide variety and small size of components used today, it can be quite difficult to know where to start. So first we're going to show you a video where Dan M0WUT shows you close up how to tackle a wide range of components from a conventional resistor to a tiny surface mount chip. And whilst this video is a recording, Dan will be here live straight afterwards to answer your queries and questions. So please send them to us using the YouTube chat either during or straight afterwards. And please include your name and your call sign if you have one at the beginning of every message. But now let's learn more about the art of soldering.
Hi, I'm Dan, Mike 0 Whiskey Uniform Tango, and today we're going to have a 40-minute look through hand soldering techniques for radio amateurs. As processes evolve and parts get smaller and smaller, in order to take advantage of the latest technologies, radio amateurs are being challenged to solder smaller and smaller parts to get all the benefits of the latest progress. So we're going to start at through-hole resistors and work our way up to some of the most challenging parts that can be reasonably soldered in the home shop. So the first tool we're going to need is our soldering iron. These come in three basic kinds: the kind that don't have a base station and plug directly into the wall, and then two kinds with base station. In one of these, the heater is in the handle and we have interchangeable tips that plug onto this heater. The second type, the heater is directly embodied inside the tip. You can spot the difference in these normally in the price and their construction. But the ones with the heater embedded in the tip tend to offer much better heat delivery, as the heater is directly connected to the tip rather than going through some sort of sprung contact in the handle of the other one. Tip shape is a matter of personal preference for a lot of people. There are a huge variety of tips out there, but I tend to use three basic ones, one of which is the chisel tip. So this is your standard workhorse tip that covers all sorts of things. You can get these in a variety of sizes, and the bigger the tip, the easier time it is going to have transferring heat from the heater and the soldering iron to your workpiece. So bigger tips are useful for soldering parts with large ground plane that are capable of dissipating a lot of heat. Aside from that, it largely comes down to personal preference. The two kind of tips that I use regularly are this J-style tip. And the reason I like this is because by rotating the tip you can effectively change the contact area it has with your parts. So you can use the back of it to get a large area of contact, or you can turn it over and use the tip for delicate work. And the other tip I like is this style of beveled tip, which is excellent for drag soldering, which is a technique we will cover later. So one area that is often debated is the wattage that you require out of your iron and what temperature to set it to. In reality, this is less of an issue than the iron's ability to deliver that heat to your workpiece. If you have an iron from a reputable manufacturer that is able to deliver a lot of that heater's energy into the workpiece, you should be able to solder nearly every task with an iron in the region of somewhere between 60 and 80 watts. The exact temperature of your iron is of less importance. I tend to do all my work at 350 degrees, and this is a nice balance between not burning the component, and I will use this for all the soldering work demonstrated today. One piece of advice I would give to beginners is to avoid using the default conical tip that comes with most irons. It allows for very small contact area between the iron and the workpiece, and thus leads to very bad heat transfer. This means you have to keep the iron on the joint for longer, or run the iron at a hotter temperature, both of which lead to suboptimal results as you burn the flux off faster. So irons such as this that will make you an excellent starter iron can be had for around £120, with the tips that are distinct from the heater coming in at around £4 or £5 each for most of them. For close to £300, you can get this style of iron, where the heater is embedded in the tip, where the tips come in at around £30 each, and this gives you a few more bells and whistles, such as the improved benefit from direct heater in the tip, and also the ability to change tips without having to handle any hot components. If you want to spend a little less, the TS100 iron can be had for around £60 and actually features tips with the heaters embedded in them, and is an excellent starter option if you're wanting to spend a bit less money. Now, as well as the metal that we melt to make the joint, another important component is flux. Flux is a chemical which cleans the surfaces to allow our solder to flow nicely over them, and also reduces the surface tension of the solder. For most amateur construction, you can get away without providing external flux, as the solder often has a core of flux running down the middle. We can see this if we look under a microscope. However, for certain more advanced soldering techniques, an external supply of flux is an absolute necessity. The additional flux can come in two main kinds, one of which is very runny and has a sort of viscosity similar to that of water, and the other is more of a gel. The runny kind is useful for general everyday work where we are using an iron. However, the gel kind is more useful when we are using hot air, as it allows a greater volume of flux to be applied. Otherwise, if we just applied a very thin layer, it would have all burnt off by the time our board gets up to temperature and not be able to be effective. As well as coming in different formats, fluxes also come with different chemistries. These broadly come under three main groups of no-clean fluxes, rosin-based fluxes, and water-soluble fluxes. Water-soluble fluxes gives excellent joints and are easy to clean off, but very easily absorb water and become corrosive, so cleaning the board is a must if you use them. For hobbyist use, I would say these are unsuitable, as they require cleaning techniques beyond the realms of the average amateur. Rosin fluxes are made from tree sap. They are not conductive themselves, but slightly absorb water over time, so can become conductive if left in a moist environment. For most circumstances, this is not a problem, but if you are doing very delicate sensing circuitry with trying to detect microamps of current, then this can become an issue. No clean fluxes are specifically developed to not require cleaning after being used. They will leave some residue on the board, but it is generally considered harmless and can just be left there. For most amateur projects, I would recommend sticking to either rosin or no clean fluxes, as they do not require professional cleaning techniques, and you can get very good results with them. When it comes to soldering, there are two main hazards that should be considered. One of which is that your parts will be at a high temperature and may take time to cool down even once you've removed the iron, so do allow adequate time before handling the parts. The main risk is the fumes given off when the flux in the solder vaporizes. We can see this that if we take an iron to the solder, we produce this white smoke, which comes from the flux. Long-term exposure to flux fumes may cause respiratory problems, so if you are doing a small amount of soldering, working in a well-ventilated area and using a small desk fan to blow the fumes away from your face will probably be sufficient. If you are soldering more regularly, purchasing a fume extractor that will pull the fumes away from your face and filter them out of the air is probably a good idea. Okay, so now we're ready to start soldering. We're going to start with through-hole devices. These are devices that have legs that get pushed through the board and then soldered. We're going to start with the simplest two-terminal device of this resistor. So what we do is we bend the legs up carefully to be 90 degrees. And then we can push our part through the board, ensuring that it sits flush with the board, and then gently spread the leads apart, and that will now hold our part in place. Now we can place our board down on our work surface, making sure that it is one that is able to take the heat that we're going to apply with soldering. Turn on any sort of fume extraction that we have, and with our iron hot, we are going to apply the iron to the pad, wait for a second, and then gently feed in the solder until it forms a nice fillet, and then take away our iron. Now we have made our connection, we need to trim the excess leads off the part. These parts may fly when we cut them, so it's important to keep a finger on top to prevent them flying. So if we just put our finger and bring our pair of cutters in, and we can now trim the excess leads off. And again. And if we inspect our board, we can see that the solder has flowed all the way through to the other side, as it should be for a good through-hole solder joint. The same techniques that we used for resistor can be used for nearly all through-hole packages. So here we are going to solder in a socket for an integrated circuit into our board. With these, in the same way to the resistor, we can place it in, either use some tape or your finger to hold it in place, taking care not to have your finger on the pins that you're about to apply solder to, and then we can tack 2 of the pins in place to hold the socket, check we have positioned the socket correctly, and then solder the remainder. One thing that is probably worth avoiding is some of the pins will be connected to your ground plane, as we can see with this one here. These pins will require more heat to solder as they are connected to a large heatsink in the ground plane of this board, so it is probably better to save these until you have got the chip positioned correctly and do while you're not holding the socket, as these will take a little longer to solder. So now we've got our 2 corners tacked, we can inspect our board and make sure the socket is in flat and level, and then we can start soldering the rest of the pins. So here we can see all of our joints are bright and shiny and have a nice concave fillet shape between the pin and the pad. Now on the other side we're going to demonstrate some pour soldering technique and show the effect that this causes on the solder joint. So for this first pour joint we're going to do a technique as seen by a lot of beginners, where we apply the solder to the iron and then apply the iron to the pad. What has happened here is all the flux has burnt off, as you can see by there being no remaining white smoke. And now when we try and make contact to our pad, the solder is very reluctant to stick and we have a hard time. Now we have applied our iron to both our pad and our pin, but we are going to hold it there for too long so that all the flux burns off inside this joint. What we will see here is that the joint will become dull and will not have a smooth shape to it. On this joint we are going to feed far too much solder in, and we will see that we no longer get a nice smooth fillet but rather a bulging mass of solder. And this pin, which we can see is connected to the ground plane, is taking a bit longer to solder. This is absolutely fine, just hold your iron for a few more seconds before feeding solder into the joint. However, nearly all the faults with these joints were caused by insufficient flux, so we can solve the problem by adding just a little bit more solder, which will add fresh flux into the joint, and then we can use the iron to pull away any large excess amount of solder. So do it with there, so we can do. Oh. It's important that we clean our iron between each of these operations to prevent a large amount of solder building up on the tip. This can be done either by using brass shavings, as we have here, or by using the damp sponge that you often get included with your iron. I tend to prefer the brass shavings over the damp sponge, as it doesn't thermally shock the iron when you try and clean it. So these techniques should allow us to solder most through-hole components. We're now going to have a look at surface mount components, known as SMD for short. Here is a selection of SMD components, along with a through-hole resistor and a pound coin for scale. This size is called 0805 and is roughly 2 by 1.2 millimeters, and is a good size for most amateurs to start with. These are available in ever-shrinking sizes. Here we have 0603, 0402 and 0201. You can also get very large SMD components. This one here is nearly as big as its through-hole equivalent. However, some of the ease of assembly of surface mount devices mean they are preferable in modern consumer devices. Surface mount soldering is nothing to be afraid of and can be done using very similar techniques than that for through-hole. However, we are going to need a few additional tools. The first of which is, because these components are so small, we're no longer able to use our fingers. Recommend picking up a variety of tweezers in different sizes, and finding which ones work best will just be a matter of personal preference. There is no need to buy expensive ones, they're all pretty much the same. You're also probably going to want some finer solder. This is the stuff we were using earlier and is 0.7mm in diameter. If you try and use this for finer surface mount devices, you will end up being unable to accurately control the amount of solder you feed into the joint and will nearly always have too much. Finer solder with a diameter less than 0.5mm is generally recommended for surface mount devices. Today we'll be using 0.38mm solder for this job. The last and most important tool in doing good surface mount soldering is being able to see your work well. This means working in a well-lit area and, for the smaller sizes, having some form of magnification. The larger sizes, such as 1206 and 0805, can be relatively easily done by eye, but as you get down to 0603 and 0402, having some form of magnification will make your life much easier. This can range in anything from simple jeweler's loupes, though these are probably best for just inspecting your work afterwards, as they require you to be very close to the workpiece, which is tricky to do while soldering. An excellent option is these little HDMI microscopes that can be bought relatively cheaply off eBay and AliExpress. These have a small screen on the top, allowing you to see your work and also to sit in a much more comfortable position than peering over your work. The ultimate option for surface mount soldering would be a full stereoscopic microscope. This allows you to have a 3D view of your work and to zoom into much finer detail. Having depth perception is a useful addition over the HDMI microscope. However, it is not a requirement to achieve outstanding results. Okay, so let's do some soldering. We're going to start with 0603 resistors, and one excellent way to get a wide range of SMD components very quickly is to buy these sort of sample books. These contain a selection of all the different values of resistors and capacitors, so you can use them in your projects. The parts themselves often come on this paper tape with a clear film over, and this is because these tapes are primarily designed for machine assembly. So, we've now got our tape and the pads where our components are going to go. We start by peeling off the clear film on the top, and we can empty some of the parts out onto our board. Now these will nearly always come out upside down, but this one here has come out the right way up. So what we can do now, with our fume extraction on, is we can apply a small amount of solder to one pad. And we want just a nice little flat bead. It doesn't worry if this joint is perfect, we'll be coming back to fix it later. Now with our tweezers we can get hold of our part and gently slide it in, and whilst reflowing the pad, and that will then hold the component in place and central. Now we can solder up the other side, and then go back to touch up the initial joint if necessary. However, this joint is fine, so we will not be going back to it. We can then repeat the process for all our resistors. So in, melt the pad, push our resistor in, trying to get it central, and bring the iron away. Again, we can just touch up the other side. And those are now nicely soldered. This technique applies to nearly all passives, no matter what size they are, from the biggest to the smallest. They can all be done by applying solder to one side, but not too much. Then gently reflow the solder while sliding the part in, soldering up the other side, now the part is held to the board, and going back and touching up the first joint if it is not looking good. So here is an 0201 part that can be soldered with exactly the same technique. So this technique that we used for two-terminal devices also works with devices with much more pins. Here we tack down a couple of pins to hold the part in place and keep it central, and then go around and solder all the other joints while the part is held down, and then touch up the initial joints in case they are not satisfactory. We're going to now attempt to solder what's called a SOIC, or small outline integrated circuit package, onto this board using exactly the same techniques as we did previously. So we're now ready to start soldering our SOIC package. So what we're going to do is we're going to apply a small amount of solder to this pad in the top corner. And so now we're going to get our part approximately positioned, melt the solder and slide the part in. This joint is not as clean and pretty as it should be, but it's fine, we'll come back and fix it later. Now we're going to move our work around, always ensuring that the work is in a comfortable position, and we're going to solder the opposite corner, and that will hold this chip down so we can solder the remaining pins. Now we've got our part held firmly in place. We can work our way along the chip, soldering all the pins one at a time, feeding just a small amount of solder into each one. We can now repeat for the other side. And going back and repeating the joints that we did earlier. If any of our joints look slightly dry, such as this one here, this is when we can use our external flux. It is preferable here to add just flux rather than applying more solder to the joint, as that could lead to too much solder being on the joint. We just run our pen down, and that has deposited a fine layer of flux. And now we can go through reflowing all the joints. And now we have nice shiny fillets on all of them. And the techniques we've just discussed for circ will allow you to solder nearly any large surface mount device. Now we're going to have a look at smaller packages where the pin pitch becomes small enough that soldering each pin individually becomes hard, and other techniques are advisable. This package here is known as SOP or SSOP, and we can see has the pitch half that of the SOIC chip. Now we're going to solder this part down onto a much smaller PCB, and this means having some way to keep your work steady is important. This board is small enough that if we just place it on the desk it would be very likely to move, so we want some way of holding it. There are several ways to do this. This is my personal favourite. It is similar to a vise, but it is much lower height, otherwise the vise tends to raise the workpiece up to the point that is uncomfortable to solder, whereas this keeps the workpiece very close to the desk, which is a much more natural position to hold the iron in. Okay, so we're going to apply the same technique as we did with the SOIC. We may accidentally apply solder to multiple pins at the top here, because these are hard to solder individually, but it's not a problem. Got a bit of solder on this top right pin. Now we're going to slide our part in, trying to keep it central. So once again we have a not particularly pretty solder joint here, but that's fine. Its job is just to hold the chip in while we solder the remainder, and this can be fixed later. Okay, and now we tack the pins in the opposite corner just to hold that down, and we can push down with our tweezers to ensure our part is nice and flat to the board. So now we're going to do a technique called drag soldering to solder the remainder of the pins. This is a technique where we drag the iron across all of the pins and it solders them all in one go. For this sort of soldering, a tip shaped similar to this one is best. as it allows you to heat several pins at once, so as you drag the iron over, the solder ball that you will form is pulled along with you, and you deposit exactly the right amount of solder on each pin. We're going to start by laying a thin line of flux across all of our pins. Now all of our pins have flux on, what we are going to do is we're going to melt a very small amount of solder onto the tip of our iron. Earlier I said that you shouldn't use this technique of applying solder to the iron and then applying the iron to the work. The reason for this was that the flux all got burnt off before it had time to work. However, because we have applied additional flux to the board, this is not a problem. What we can do now is, keeping the iron flat against the board, is we can apply solder starting at one end, and we can then drag our iron along the board, soldering each pin as we go. We now have nice solder joints on most of these end ones, however these two on the end are not looking nice. If we go back, we can now apply a bit more flux to just the problem area, and applying our iron again, we can ensure that a good joint is made. We have now successfully soldered all the pins on this side of the chip. The shininess you can see here between the joints is just flux residue. This is not solder shorting between the pins. Now we can go and solder on the other side. So we take our flux pen, we apply a nice line of flux to all of the pins, and these two here which are previously shorted will be tidied up in this process. So we put a small blob of solder onto the end of our iron, really not much, a little bit more. And now, keeping our iron flat, we can just go along. There we go. And we have soldered most of the pins. We shall just touch up this one at the start. And remove this residue here. And now we have successfully soldered all this chip. So once we can do drag soldering, we can now solder pretty much any part that has leads on it. To demonstrate this, we're going to solder a large quad flat pack. So this is a large 208 pin device with pins on all four sides, but the techniques we're going to use will be exactly the same. And now we can inspect our joints to make sure they've all been made properly. Okay, all of our joints are nice and shiny, and we can go on and do the other three sides. If you apply too much solder to your iron before starting this, you'll find that the pins have a tendency to short each other, as the iron is unable to drag the excess solder off the pins. So if there is a small amount of solder bridging, we can just use the iron to redistribute the solder among the pins, and hopefully we can get away with it. So we can apply more flux. Note that once we have used flux once with the iron, we should really apply a bit more. So we apply flux over the joints again. And now what we're going to try and do is drag that solder ball along the pins and see if we can distribute it. I'm going to keep using the brass wool to clean the excess solder off the iron so we can keep collecting more. This has got rid of a good amount of the solder, and repeating again. If just a couple of pins are bridged, instead of dragging the iron along, you can just drag it off the side and see if that will pull the solder with it. It's important to not apply too much pressure whilst dragging the iron along the pins, otherwise you could bend pins or damage the traces on the board. And now we have fixed our solder joints. For this sort of soldering, having external flux is absolutely essential. We've burnt off all the flux in the solder on the iron, and this will lead to incredibly poor joints if we do not use any. Here we are going to try without some to demonstrate what happens if you do not have sufficient. I've got no idea what's going to happen here. So here we can see the iron was unable to pull the solder off onto the adjacent pins, and what we have is a lot of shorting. However, again, we can fix this just with the application of some flux. And there we go, we've repaired all our joints. Okay, so now we can solder nearly all leaded surface mount devices. However, some parts do not have legs and have pads on the bottom. Taking this as an example, this is a QFN, it stands for a quad flat no leads package, and has one large pad on the bottom with 16 pads around it. This pad is very hard to solder with the soldering iron, because although you might be able to touch the 16 pads around the outside, you'll be unable to get good contact with the large central pad in the middle as it's under the chip. So instead, what we're going to use is a hot air gun. This works by blowing hot air onto the part and the PCB, and will then reflow the solder, attaching the part to it, including in places that we can't reach with an iron. We can then use an iron to ensure that all the joints around the outside are good if we want to check. So unlike soldering irons, where there are different types of heating, hot air guns all pretty much work the same way and only really have two settings, that is temperature and the speed at which the air comes out. Finding the right settings for your particular hot air station is entirely personal. However, a starting temperature of around 300 to 350 degrees is probably a good start. So here is the part we're going to solder. We're going to start by applying solder to all of the pads, starting with the large pad in the centre. We want to have a small amount of solder on this, but enough to cover it. If we have too much solder on this pad, the chip will float on top of this bed of solder and won't make contact with the pins around the edge. This looks like a good amount. Now we can apply solder to all the peripheral pads. It's usually a good idea when soldering either QFP or QFN packages to focus on those first, as this gives you as much space around the part to work as possible without worrying about hitting other parts. Now what we can do is we can take our gel flux, and gel flux, as we said earlier, is definitely preferable for this. The watery kind that comes out of the pen will have evaporated long before the hot air has got the board up to temperature. So we now apply a small amount in the centre of our part. Now this is probably excessive amount of flux, however it is generally better to have too much than too little. Too little will lead to bad solder joints, whereas too much just means we have to do more cleanup afterwards. So we can now use this flux to stick down our part, noting the orientation, and we can push it down, and now we are ready to start using our hot air gun. The one I'm using today has a bent muzzle, as this allows for easier working under a microscope to achieve even heating of the part. So we're going to start gently heating our board from around 3 inches away. If we're too close, what it'll do is it'll blow the part away, and we don't want that. And now we make small circles to ensure the board is heated evenly. It doesn't matter if the part isn't perfectly aligned now, it will self-center later. We can now bring a hot air gun closer and closer into the part to heat it up further. We can now see the joints starting to refloat and the part being pulled into place, and with a small tap down to ensure the part is correctly seated, we can see all the joints float, and the solder actually pulls the part in, as we can see here. It's important to press down to ensure that any trapped solder underneath is released, and then we can bring the iron away. And we can see here that we had a little bit too much solder on the central pad, which has now squeezed out and caused these two pinches to be shorted. This is easily fixed. We can apply a small amount of flux around the chip, having ensured that we've let the chip cool down enough that the solder is fully set. And now we can use our iron to go in and check that all these joints on the outside are properly formed. This is the nice thing with this J-tip, is that we can use the back of it to check our solder joints, but also use the point of it if we wish to individually inspect each one. And now we have successfully soldered this QFN package, and this technique works for all QFN packages. You just have to be slightly careful on the larger ones that you achieve heating over the whole chip rather than just in one small area. So I've done this with leaded solder, which does an excellent job of pulling the part into position. If you use a lead-free solder, you may have to manually position the part, as the self-centering action is not as strong. So the techniques we've discussed today should allow you to solder most through-hole and surface mount devices. The two packages that we haven't discussed today are LGA and BGA. While these can be soldered with the same techniques as we have discussed for QFN using hot air, because these parts have a large number of pads underneath the chip, inspecting them is generally out of the reach of a radio amateur. Professional assembly lines will use X-rays to inspect these parts, and this is outside the realm of the home constructor. We used flux as an essential part of making all our solder joints. However, the use of flux tends to leave residue on the board once we have soldered using it. No clean flux means that the residue is completely harmless and could be left on the board. However, we were using rosin flux, and it is better to clean it off, A, from a visual point, and B, to ensure that it doesn't absorb moisture over time. The easiest way to remove flux is with some sort of absorbent material, such as this foam swab, and isopropyl alcohol. Now, cotton buds are not suitable for this task, as they will tend to catch on components on your board and leave strands of cotton fibre all over your board. So we can soak our swab in IPA and now use it to remove the flux from around our part. And we can now see the joints more clearly. The IPA we've used will evaporate naturally. However, if you allow it to evaporate, it will tend to leave all the flux that it has removed from your component just on the board wherever the alcohol was, so it is better to mop it up with something absorbent, either just using the absorbents of the foam swab itself, or by use of something like paper towel or some sort of lint-free wipe. And now we have our nice clean board. If the flux has been burnt on more or a larger quantity of it, special flux cleaners can be used in exactly the same way. These tend to come with these little brushes on the end that can be used for more aggressive scrubbing. And once again, this needs to be absorbed off the board. We can either use a paper towel, as before, to nicely clean our joints. Paper towel is generally good but tends to leave a small amount of lint, so I tend to just finish with a foam swab to remove any last traces. And now we have nicely clean joints. Instead of applying solder to the board and then using flux to help us reflow it, we can also use a substance called solder paste. Solder paste is a load of tiny little balls of solder suspended in flux gel. This can be applied to the board using a solder paste stencil. This is a very thin sheet of steel which is then laser cut to have apertures for where we want solder paste to be on our boards. We can then press a layer of solder paste over this stencil similar to screen printing, which will leave solder paste deposited on our board above our pads. We can then use either an oven or hot air to reflow the board similar to the way we soldered the QFN before. And there we have it. We've covered techniques that allow us to solder from large through-hole components to all but the most advanced of surface mount devices. I hope this gives you the confidence to go and try out using smaller packages in your designs. The one piece of advice I would give to beginners is that it's important to be able to see your work, so getting good magnification is the biggest piece of advice I can give you. Thanks very much, and 7-3.
There we are. What an introduction to soldering. It's an amazing covering from that basic resistor right up to the latest small chips and things. And I'm really pleased to say that we've now got Dan coming to us live from the National Radio Centre at Bletchley Park, out in the nice sunshine, I think. Hello, Dan.
Hello.
Good to see you, and thank you very much for that wonderful video. I've had lots of comments already from people appreciating it, but got a few questions as well, so hopefully you can help us answer some of those. I think generally, I'll start with one to say, where do you buy this stuff? I know you did mention things like AliExpress in the video, but you know, it's not always accessible to all of us. And of course, Maplin, the UK retailer, is no more, so there's nowhere on the high street you can go and buy a lot of this equipment. So where do you recommend in the UK, as well as some of the Chinese suppliers?
So, of course, with the UK, you're going to pay a premium for them having done the trouble to import it. So, if you're wanting the lowest cost, I stick with AliExpress. In the UK, places like Farnell, CPC all have online web shops that you need. You don't need any sort of business account to trade with. They will trade with you like anyone else, generally next day shipping. Yeah, those tend to be the ones I go to. Other than that, hunting eBay for people selling equipment that is no longer makes commercial sense but still has plenty of useful life in it is also a good place, but you sort of have to wait for the right opportunity on that.
Yeah, okay, Dan, thank you. I mean, we've got Farouk Taj says, Dan, there are so many options when it comes to choosing a soldering iron station, a hot air gun, solder, flux, etc. Is there a recommended list or suppliers to help us choose what to invest in? So I guess they're the ones that you recommend.
Yeah, so hot air, I tend to find a much of a muchness. You know, hot air is hot air. I find soldering irons do have more variability. There's the brand names that you sort of see in industry. You sort of get your Hakko, your JBCs, and your Metcals, but they're really at the premium end. But there are excellent options. The sort of TS100 and TS80 are being hugely popular. For soldering and flux, all I would say is buy it from a reputable supplier and try and get a decent brand name, sort of Multicore or Loctite or something like that, because those things do have a shelf life, and a lot of those that you can find on eBay have often expired there. But ultimately, it tends to come down to finding one that works for you, and sort of, unfortunately, you know, picking a name brand reduces the risk of going wrong, but there will be a bit of trial and error involved in that.
Sure, okay. Thank you. Pete M0PSX from Essex Hams, he says, what's your thoughts on lead-free plus or versus leaded solder?
So, for personal projects which are not going into high volume, I tend to prefer leaded. It is easier to work with and is more forgiving. That sort of self-centering action that you saw when reflowing a QFN, you don't get lead-free. It just tends, when the solder melts, it just tends to sit there. So I find leaded is much more forgiving for the amateur. Of course, for anything that was being taken to production or sort of produced in high volumes, then I'm absolutely an advocate for lead-free, but for someone starting out in construction, I think having all the help you can get is worth it.
Okay, Dan, we've got a little bit of breakup with the internet there, but I think we got the message. Thank you very much indeed. I mean, someone's asked specifically, I ought to just ask you, the Hacko FX888, do you mentioned for about £120? He's saying he normally sees it for about 150 or so. I mean, do you have a supplier for that you recommend? I think we may have lost Dan, actually. That's a shame. I don't know. Just looking to Tammy to my left, who's doing all the technical operating today, but I think Dan's signal has completely frozen on us now, which is a shame. But I think, oh no, we've got him back maybe. So Dan, can you hear us? We'll cut back to you. Dan? You're looking at me or us, but I don't know if you can hear me. Can you nod if you can hear me?
Yes, sorry about that.
Okay.
Yep.
I'll ask the questions very slowly and carefully. As I said to you, lots of the comments, though, coming in, just what a great demo and things that you've done, because it has taken us through all of the soldering and things like that. Someone asked you to recommend solder brands. I heard you mention Multicore, which is something that I've certainly remember from my young days. There's other companies, aren't there, like Wharton and things. Any other solder brands, and particularly Fluxes, actually, because they're not so well known. You said use a good Flux and a good supplier to make sure it's fresh. Any brand names come to mind?
There are cheaper versions. There is Chip Quick. There is MG Chemicals. Off the top of my head, both of which I've used before in the past, but it's as much avoiding the sort of no brand or, manufacturer's own brand, from your distributor. Those tend to be, I'm not saying they're all low quality, but the risk of getting something that works less well for you is a bit higher. And the cost of sort of Flux does tend to be fairly high, but you tend to get much more than you can possibly use sort of within the time frame. So what we tend to do as a club is we tend to do a group buy of the Amtech stuff and sort of split it between 5 of us. And at that point, it makes it much more palatable to sort of swallow the bill.
Absolutely, yeah, that's really good advice. Thanks, Dan. We've got a reasonable connection with you now. So I'm going to ask you this while I can. Michael Naylor has asked, is it worth using a heater to keep the PCB warm? I hope Dan got that question. I'm not sure. Dan, did you get that question?
It depends. Keep it warm during what? You certainly can get about to reflow apart and then use a hot air. Yeah.
Sorry. Yeah. It's very, very slow to you. Yeah, the question was, do you have to keep the PCB warm? I think that probably means warm it up before you do it. Sometimes in commercial soldering, you certainly keep boards in an oven, don't you, just to keep them moisture free and also to pre-warm them. So that's probably the question.
Yeah, and they are. That is sort of the proper way to do it, in that it reduces thermal stress on the board. You sort of more evenly heat the board up and then just use hot air to sort of tip it over the edge to get the solder to melt. Personally, I've never quite justified the expense of one, and I'm fully accepting that the stuff I build, it is not ever going to end up on a sort of a rocket or anything high reliability, in which case, it's a whole different ball game. But I think the answer is technically yes, but you can get away with it I've never had a problem not using one.
Okay, Dan, thank you. Not probably a question maybe you can specifically answer. It was talking about RSGB X308 October 20. Doesn't have the resistor color code multiplier. Is this correct? I'm not really sure. That's Ulistar 95970, but we'll look into that for you. Normally the multiplier on a color code is that last color, isn't it? Generally nowadays gold or silver to represent 5 or 10% or something like that, but we'll try and get back to you on that one. So a couple of people actually, interestingly, Dan, I didn't know this, but RS refused to sell leaded solder or paste to individuals. But I know, in my experience, you can certainly buy it easily from places you mentioned, Rapid Electronics, CPC.
Yeah, I think the last place I got mine from was Mouser, and they didn't really. I'm certainly Mouser and Farnell in the last year have supplied it. I didn't know about RS.
Yeah.
Not doing that. So thank
No,
you for the info.
Yeah, thank you very much. Well, Dan, I think we're nearly there at the end of this Q&A, because we're coming up towards 11 o'clock and we're going to go back to the NRC where you are, I know, but we're going to go back indoors in a moment. So I'd like to thank you once again for an excellent video, really good tutorial which people will be able to, I'm sure, look back on and refer to, and I'm sure you've inspired lots of people to give soldering a go. And if we're used to just the traditional sort of conventional components, I'm sure it's given people confidence to have a go with some of this surface mount. So Dan M0WT, thank you very much.
Yeah, my pleasure.